Next is a rank booster question from desorption activation energy asked in December 2024. So earlier these type of questions were only asked in GATE, but now as you have access to the calculators in CSIR exams as well, you get numericals in NET exam as well. Okay, so let's try out the question. The average time for which a hydrogen atom remains adsorbed. So the data which is given is of gamma on a surface is 35% shorter at 1000 Kelvin than at 600 Kelvin. The activation energy in kilojoules per mole for the desorption is closest to. Okay, so based on what we have already learned, let's try to solve it. We already know that gamma 1 is gamma naught a to the power, gamma naught e to the power EA by RT1. Now see, there are two temperatures given. Let's consider 600 as T1 and 1000 as T2. So we'll take this as equation number 1. And about gamma 2, gamma naught e to the power EA by RT2. This is 2. If I divide 2 divided by 1, what I get is gamma 2 by gamma 1 is equal to e to the power EART2 minus EA by RT1. And this EA is what you have to find. EA corresponds to the desorption activation energy. Desorption activation energy, right? Now, if I take ln on both sides, natural log on both sides, what I get is ln of gamma 2 by gamma 1 is equal to EA by R into 1 by T2 minus 1 by T1. Easy. Now see what is given in the question. You have to find the desorption activation energy in kilojoules per mole. So if you have to find it in kilojoules per mole, the unit of R that you'll be putting will also be in kilojoules per mole, 8.314 into 10 to the power minus 3 kilojoules per Kelvin per mole. T2 is the temperature, 1000 Kelvin. T1 is going to be 600 Kelvin. And gamma 2 by gamma 1. See, already they have given that gamma 2, which is the residence time at 1000, is 35% shorter than that at 600. So what does it mean? It means that gamma 2 is equal to, initially it was gamma 1, and then when the temperature got increased, it reduced by 35%, right? Now, 35% in numerical value means 0.35. It is reduced. So you have to subtract 0.35 gamma 1 from gamma. That's it. So gamma 2 is equal to, when you subtract this, you will get 0.65 gamma 1. So you can substitute that. What do we get? We get ln of 0.65 gamma 1 divided by gamma 1 is equal to EA by 8.314 into 10 to the power minus 3 into 1 by 1000 minus 1 by 600 is what you get. Gamma 1 and gamma 1 gets cancelled. Here the temperatures are in Kelvin. So the Kelvins over here, the units, kilojoules per Kelvin per mole, right? So per Kelvin and Kelvin also gets cancelled. And at last, what you have is in kilojoules per mole. So you can rearrange this. Okay, I hope you understand how Kelvins got cancelled. I hope so. So that is, I'll show you once. Ln of 0.65 is equal to EA by 8.314 kilojoules per Kelvin per mole into 600 Kelvin minus 1000 Kelvin is 400 Kelvin. I'll write it like that. Minus 400 Kelvin divided by 1000 Kelvin into 600 Kelvin is what you have. So initially, this Kelvin and one of the Kelvin from the denominators get cancelled. And next, you have per Kelvin over here, and you have a Kelvin left over here. So whatever you have remaining is just kilojoules per mole. This is what you have, right? Now you can rearrange this. EA is equal to 8.314 into 10 to the power minus 3. You take this here into ln of 0.65 into 1000 into 600 divided by minus 400. You can calculate this. See, ln of a value which is less than 1 is going to be negative. So this negative and the negative sign over here gets cancelled. And finally, the value of EA that you're going to get is 5.37 kilojoules per mole. In the question, they have asked us to round it off to the closest value among the options A, B, C, D. In option D, you can see 5.4. What we have got is 5.37, and hence the correct option is option D. All right. So I hope you have got an idea now. We'll see you in the next.